What is a double pipe heat exchanger? A double pipe heat exchanger, also known as a concentric tube heat exchanger, consists of two concentric tubes, or pipes, of different diameter with fluid flowing through both the inner tube and the annulus. The tube can be oriented in a countercurrent flow setting, where the fluids flow in opposite directions, or co-current flow setting, where the fluid flows in the same direction. These will be discussed in greater detail later. Double pipe heat exchangers are one of the simplest examples of a heat exchanger.
What is the purpose of a double pipe heat exchanger? The purpose of this mechanism is to maximize heat transfer as economically as possible. There are other heat exchangers that are more efficient, but they can be far more expensive. Concentric pipe heat exchangers are typically used for low to moderate flow and heat transfer rates. Fluids are generally in the same phase and do not experience any phase change through the system. Some examples of applications of concentric tube heat exchangers include material processing, food preparation, and air conditioning.
What is co-current flow? Co-current flow, also known as parallel flow, is a configuration where both fluids are flowing the same direction through the heat exchanger. This configuration is useful when a limiting temperature is desired. Because the fluids flow in the same direction, the outlet of hot fluid can never be lower than the outlet temperature of the cold fluid, and vice versa. This is ideal when one is trying to avoid a phase change through the exchanger. The disadvantages, however, of a parallel flow are greater thermal stress due to greater initial temperature differences, which can lead to vibrations in the system, and the overall larger required area of the system.
What is counterflow? Also known as counter-current flow, counterflow means that the double pipe heat exchanger configuration is set up such that the flow through the inner and the annulus are in different directions. In this configuration, the temperature difference calculated below as the log mean temperature difference, or LMTD, is larger than in co-current flow configurations. In the next slide, we will discuss how to calculate heat duty, and it will be shown that the larger the LMTD, the larger the amount of heat transferred. Since this configuration yields greater heat transfer, counter-current flow is considered the preferable setup for a double pipe heat exchanger.
How do you calculate the heat duty for a double pipe heat exchanger? There are two methods that a person can use when solving for the heat transfer rates of any double pipe heat exchanger system. The traditional method is to use the LMTD method, as discussed on the previous slide. The newer method is to use the NTU effectiveness method. It should be noted that both methods of analysis will yield equivalent results. When using the LMTD method, the fluid properties such as density, kinematic viscosity, and thermal conductivity at the inlet or outlet temperatures must be sourced, and pipe dimensions must be measured. With this information, the Reynolds number, Nusselt's number, and Prandtl's number can be determined, and it allows us to calculate the convection coefficients for both the inner and annular pipe. With that information, we can calculate outlet temperatures or inlet temperatures, the log mean temperature difference, and the heat balance of the warmer side, the cooler side, and the overall heat transfer. Ideally, they should all be the same, but we do not live in an ideal world.
What pressure losses are generated by double pipe heat exchangers? An advantage of double pipe heat exchangers, being straight pipe with entrance and exit fittings, is that they generally have a lower pressure drop than other common heat exchangers. To calculate the pressure drop across the heat exchanger, for either the inner tube or the annulus, the flow regime, either turbulent or laminar, must be determined. The flow regime, along with the roughness of the pipe material and pipe diameter, is used to determine the friction factor. Together, these characteristics are used in the equations below to find the pressure drop experienced by the fluid. Cost savings can be realized by using a heat exchanger, such as a double pipe heat exchanger, that keeps pressure losses to a minimum.